Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about calling out Linus tech tips, specifically his water cooling series. So let's dive deep into it. Now, what exactly is the problem? Well, he made two videos. Like, this was the first video that I was very triggered, quote unquote. This is the second one. Just like when I'm making this video, this is 4 days old, and I was like, no, this had to be basically. Problem is, what he's doing is awesome, but how he's doing is very inefficient. There is a efficient and easier. Let that be very clear. It's not gonna be like, oh, it requires PhD and all that. No, it's efficient and it's easier. It's less quote unquote jank. So that's the whole point. And they tried to cool two things: mechanical room, which had like servers and electronics and all that stuff, and server room for one of the badminton center. So it works, but here's the deal. It looks low cost. It's not really low cost. Anyway, he gets basically unlimited supply of PC parts, but does not mean like, look up the price of car radiators. It's not that cheap. Look up the price of Corsair fans. Yeah, you will be shocked. And the amount of piping, plumbing, and like so much stuff was done. It was like, yeah, it's one of those things. It's like when you start, it feels like, oh, it will be done in like, a jiffy. It's a very low cost. When you actually do it, it's like, yeesh. Like he was talking about like titanium heat exchanger. I'm like, unless Canada has its own supply of titanium heat exchangers are expensive. Like, I do not know what exactly, like what level of cost, but it's not cheap anywhere. So that's the problem. So what went wrong? So why exactly? There is a proper way of doing it. Meaning, if you have a scenario where you have hot place, for example, I used to work in a 3D game studios and they had a UPS unit, as in double conversion UPS. Now, double conversion UPS or online UPS, those puppies heat up a lot. Why? It's always taking the AC mains that is coming from the grid, converting it to DC, then remaking basically three-phase pure sinusoidal wave output. Now, benefit of that: quality. Side effect, it's always burning energy off. So even at 98% efficient, you have 2% heat load raw all the time. So if it's like a 5 kilowatt, you could have like a few hundred watts of waste heat all the time. So if you have office something like this, like the office I had, it's like one big unit and boatload of batteries. So in those scenarios, it's hot, and that place was so hot, so they had to have an air condition just so the UPS does not heat up. So it's a common situation where people have to solve this, that they have a place that is hot, but they have to make sure it gets cooled. So a lot of people in multiple sectors would have benefited if Linus Tech Tips would have done a proper way. Because right now, what Linus Tech Tips did, and they show it to him, to their boss, it's like, hey boss, we should do this. It's like, yeah, no. So that's the whole point. It would help a lot of sectors, specifically hotels. Why? They require a boatload of hot water for laundry services. Hospitals, ludicrously large amount of hot water. Apartments, large apartments. Generally, small one will not make sense, but it can be done. And basically, what is the final intent? What is the better way, and what will we gain out of it? Well, reduce component count. Engineering's rule number one: less component equal awesome. You always want to reduce component. You do not want to have a scenario, again, from a visual point of view, gimmick point of view, it's one thing to show. It's like, oh, we have a radiator and we have 12 fans. Yeah, that's like, if you show it to engineer for actual production use or actual, like, this is serious thing, yeah, they're gonna put a RPG up your ass. That's not how it works. Like, if you really want like uptime, you will have one push fan, one pull fan, and one should be enough to carry the whole load. So you will have two redundant power supply, and that's how you're going to make sure that you have high uptime while reducing component count. It would be very easy to service, and sometimes people do that. So like, they will service one fan, another fan is keep running, and then it's like, that's the whole point. So you always want to reduce component count. So that's why there's a lot of hunger for a better solution, but he did not show it to people, and he has ludicrously large reach. Whether you like it or not, he's huge. And I'm watching him for freaking 10 years. Like, when he was in LTT, that's how old I am. I watched it so long ago, where he was actually doing 4 Gbps was a big deal. Like, he had a LAN card, it's like 4 1 Gbps system. It was like, whoa, for back in the NAS days. So that's why, like, there is a better way of doing it, and a lot of people need to do it, but they do not know. They are not aware of it. Because again, engineers do not go from their college to other people like, you have this problem, solve it by this. You need a marketer. LTTT would have been awesome marketer. So specifically in the server video, they are talking about like, oh, I have a 3-ton AC. Now here's the deal. Ton rating of air conditions is what we call hopes and dreams. It's not real. Now like, wait a minute, what does that mean? Well, here's the deal. This is the refrigeration cycle. Does not matter what pressure it is, does not matter which refrigerant, the core remains the same. You have evaporator, you have condenser, you have compressor, and you have expansion bar. Done. How does it implement? How many what is the PSI? Like for example, this from Danfoss company. So this is 1 bar on evaporator side, and that is 7 bar on the condenser side. That will change depending on the refrigeration agent you are using, but core will remain the same. So this core has one core component, meaning pump heat from A to B. And the reason why we use this is simply because this allows us to do more than one. What does that mean? That means 1 kilowatt of energy goes into the compressor. It can pull more than 1 kilowatt out of here. Generally, in good scenarios, it will be 3 kilowatt of thermal energy will be pulled out of here and dumped on that side. So that means you will get 2 kilowatt of cooling, COP, coefficient of performance, meaning this will cool down while you are pulling heat. And the reason why we want it so much is because we can dump it in hotter environment, meaning outside air in India could be hot. So let's say outside air is 50 degrees Celsius. Yes, it does get that hot. And you want to keep your room at cool temperature of 25 degrees Celsius. That means you want to take heat from 25 degrees Celsius to 50 degrees Celsius. That's like a positive delta. It's like, bro, you have to push something that high up. We use heat pumps because, like, again, this refrigeration cycle is a heat pump. It's because it can do that in reverse gradient, meaning the hot outside is hot and yet you can still take the heat and dump it in hotter environment. Basically, you can make hot even hotter while keeping one side cool. So it works. Now, here's the deal. That COP, basically coefficient for how much energy you are carrying, it's not fixed. You would think, oh, what about refrigerant? What about sizes and all that? No, it's like it's optimum. Of course, there will be based on refrigerant gas, there is some upper limit how much you can create temperature delta, how much heat you can move from A to B. But remove all of those things do not limit you. What limits you is what is the delta. For example, if the indoor wants to be 25 degrees Celsius, out as in like you set it to 25 degrees, outdoor is 50 degrees Celsius, you'd be lucky to get 1.5 COP. If you had any access to Indian ad a few years ago, there was like a lot of push with advertisement is like new air condition, it can work at 51 degrees Celsius. We had a scenario where like a lot of air conditioners simply stopped working. It's like they were doing like electrically everything was working, they was just not pumping heat anymore. The condenser was like, I give up. The gas mixture and all that, yeah, it was like, I'm out. I'm out. So that does happen. So at 1.5 you're like, wait a minute, that means only 0.5 are cooling. Yeah, that's the whole point. So if you're like, hey, I put 3-ton AC or I put 5-ton AC, yeah, that's not actually a good system. Now, what about servers, like actual servers, data centers and all that? Yeah, that's why they have to have a thermal engineer who does the actual calculation. It's like, okay, what is this location's data? What is the air temperature here? What is the humidity here? All of that data has to be calculated and computed. Only then they're going to figure out this, like, what is the requirement, and requirement generally would be in watts, as in like kilowatts. And then they're going to figure out the compressor and they're going to buffer it up. They're going to have evaporations because there will be those extra hot days. So in those extra hot days, the condenser side, they will just simply start spraying water to keep it like chill. So COP is requirement, and you cannot get COP because that would be like at 31 degrees Celsius and this percent humidity, is the COP would be this much. At this, like, it has to be a complex chart. So companies just assume, depending on location, just assumes. For example, for us, it's around 2 COP. They assume at least 2 COP you should get, hopefully, most of the time. But like in Canada, it could be as high as 3. So you have to read up the legislation of that location. Every location is a bit different. So that tonnage is directly calculated based on default fixed value of COP, 3 or 5, whatever have you. 5 is like very large industrial units. So that's the biggest issue. That's why even if you think, oh, I have basically giant air conditioner, does not mean it can actually cool as well as you think. For human body, it's not an issue. We have barely 100 watt of heat load. But like for a server that is like going all out, like for few kilowatts continuously, yeah, even ACs are like, whoa, 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 whoa. The COP drops too much. Another aspect is, if you have a scenario where heat can be dumped out, the condenser reaches its upper limit, meaning this condensation requires you to dump heat. How fast can you dump heat? Well, you have 1 bar of atmosphere, as in the condenser is coupled by gas. The cooling medium is gas. That's the weak link. Meaning, if you have a very hot environment, let's say India's like worst is around 55 degrees Celsius. Yeah, the condenser is like, bro, air is at bit lower basically pressure. Like air literally goes down in pressure if it heats up so much. Look into planes have to be grounded if runway heats up too much. I did not knew this. This happens. If a runway gets too hot, yeah, and because plane would be like, bro, there is not enough air density for me to create safely. Let that be very clear. In emergency, they can do it. It's just like, it's not safe enough where it's like, okay, engine can actually produce enough thrust reliably. So same thing happens here. Condensers are like, you could be like, okay, this system is sized perfectly. Outdoor conditions still would be limited by the fact that condenser is trying to dump the heat into air. Air is not a good medium. It's not a good medium. That's why, like, when we have to cool turbo generator, that is cooled by hydrogen, because again, it's a better conductor. On top of that, that alone is not good enough. Like we have CO2, nitrogen. Nitrogen is good, but not that good. Not that good of bouncing momentum. Lightest bounces the most. That gives you the most conduction. To solve that, we have to pressurize turbo generators, like very high pressure of pure hydrogen. Only then you can move enough heat using gases. This does not have that luxury. So this becomes the weak link. Even if your compressor is like, I got this. A refrigerant mix, I got this. Everything else is working fine. And evaporator side, you do not have to worry too much about it, because generally refrigerant boils at very low temperature, minus 20 degrees Celsius, minus 40 degrees Celsius. So you do not have to worry about it. That creates enough delta that's like, bro, I got this. That's like, bro, I got this. That part does not get this. That's the weak link. So what does this translate to? For example, right now there is a lot of push for heat pumps. Rather than using just raw heaters, use heat pumps. It will give you, basically you will spend less energy on electricity and you will get more oomph out of it. So for example, if you have 60 degree Fahrenheit, do not ask me why it's in Fahrenheit. That's the best I could find. 60 degree Fahrenheit outside, and you need to heat up your room to a fixed temperature. You're gonna get COP of 4.3, meaning if you put 1 kilowatt of energy inside, you're gonna get almost 3.3 kilowatts of extra free energy being pulled from the outside. So it's far more efficient. But here's the deal. What happens? Temperature drops. You see the COP dropping? So at 0 degree Fahrenheit, COP drops to 2.2, meaning you are only getting double. Now, is it worth it? Obviously, double. But if in cooling, when you are talking about like 10 kilowatt or 20 kilowatt, yeah, that's no longer impressive. So, and be mindful, that is 0 Fahrenheit. It can go in negative of Fahrenheit. So at that point, it's like, what the hell you want to do? So that's the limit of air conditioner. The condenser is limited by the fact that it has to dump a lot of energy into a medium that is not very suitable for it. And the temperature gradient that is inside and outside, if that is high, the COP drops so much, it's like not really useful. So that's the weak link. That's why server room was not acting accordingly. So what is the solution? Solution is very simple. Heat pump water heaters. Now, why is that? Well, here's the deal. If you do heat pump water pumps, let the heat pump, AC is also heat pump, but AC has to dump that energy into air. Here you dump that energy into much denser medium known as water, H2O. This puppy has ludicrously high thermal capacity, and because it's a liquid, it's very high density, meaning it can easily, even from a small surface area, it can leach a lot of energy, and that's why we use liquid cooling. So temperature delta would be positive in this scenario. For example, let's say Linus Tech Tips is like, bro, I need to heat up my home using hot water, or maybe just want to use hot water for shower. How hot that would be? Let's just say 40 degrees Celsius. If you watched his thermal camera video, you're like, hey, the outside exhaust was 60 degrees Celsius. Let's say you want to cool it down, like you want to like really cool it down. 50 degrees Celsius, more than good enough. But here's the deal. The outside is lower than you. You are at 50 degrees Celsius. The medium that you want to heat up only needs to go to 40 degrees Celsius. It's a positive delta. It's super easy to do. Air compressor is like, this is my lucky day. It's like, oh, there is a hot here and there is cold there. Hot wants to go there, but delta is not high enough. Basically, if you have temperature delta, let's say hot is 30 degrees Celsius and the cold sink, as in swimming pool, is only 25 degrees Celsius, heat naturally will not flow that well. But there is a lot of desire to flow. Put a heat pump there, heat pump's like, go. How much go? Well, around up to 10 COP is achievable. 10. Meaning you put 1 kilowatt of energy in, 9 kilowatt will be sucked out. That's profit. That's why. And why it is so high? Great coupling efficiency. You're not changing the science behind it. All you're doing is improving the coupling, specifically on the condenser side. Condenser is now able to dump heat into something that takes a lot of heat to change temperature. So if it's like water is at 20 degrees Celsius, it's going to take a boatload of energy. Like that's why we use kilowatts of power rating when we are sizing up water heaters. It takes a boatload of energy. You're going to dump energy into it. It's like, and more into it, even more into it. And it's like, okay, so coupling efficiency improves. Another aspect is thermal capacity, meaning not only you are able to conduct far more efficiently compared to air, you are also has the luxury of that it takes a lot of energy to heat up. Another aspect is, which I'm genuinely shocked, is like free room dehumidification, meaning if you take this system, this is from a Canadian company, this is from a Canadian company, this is from Indian company, this is from Chinese company, it's a common thing you can just buy. You put this indoor, it has a drain pan where you can drain the liquid out wherever you want to. It dehumidifies it, meaning your place is dehumidified. You do not have to worry about it. So not only you are saving electricity, because again, you are getting very high COP and you are controlling the temperature, it's cooling down. You get hot water to use. Again, hotels will use it for laundry, hospitals will use it for laundry and some other sterilization applications and things of this. And again, in winter, you're like, okay, you can still take the heat from one place, dump it into useful place and be awesome. That's why I said, like, there is no jank here. Like, you can just go to a hotel manager, it's like, hey, you have a mechanical room, here's the deal. Just buy this system, put it there. Nothing fancier than that. Of course, do water plumbing, but I'm reasonably sure people competent enough to run a hotel knows how to deal with plumbing, or at least know who to call to deal with plumbing. And plumbing in case of Linus Tech will be a simple switch mechanism where it's like, okay, first you heat up the hot water tank. Once it's completely done, as in like temperature reaches where it needs to go, then it's like, okay, let's switch it to swimming pool. So that's the whole point. It's just hot water plumbing. That's super easy, super doable. Imagine this way, like you have a basically hotel and you're like, they also need online UPSs. And again, many times in India and abroad also, they have high voltage transformer indoors, as in they have a power line that is coming that could be around, let's say, 11 kV to 33 kV. That transformer is huge. And again, transformer loses efficiency if it heats up. So if at 40 degrees Celsius, it, let's say, would be X percentage efficient. At 60 degrees Celsius, the efficiency drops. So you can see into substations, they have giant fans for those transformers. You do not want your transformer to be hot. Here's the deal. If you put it there, transformer chills. You're like, got this. And you have a lot of other things, like for example, circuit breakers. Yeah, that does consume energy a lot. And you, again, one circuit breaker does not make enough heat. Put 50, 60 of that, you're like, this place is unnecessarily hot. Yeah, that's why. Put it there. Like again, here's, you have two component. This is single component. You do not even need to worry about two things. It's just like one thing. It has AC component built here and water tank built bottom. One thing. You just buy one thing, plonk it there, connect to the water line, done. Go home, sweet dreams. This is the most, and again, this is a smaller unit, this is a big daddy unit, these are commercial units. So commercial unit, right, think of this way, like this can work in a very cold environment. While it's snowing outside, it can still leach energy out of that and give you hot water. Imagine how efficiently this puppy will work if you put it where you have waste heat. That's why I was so frustrated. It's like, just put a heat pump. You can buy this. This is from Canada. You can buy this. This is from Canada. And again, you get to control. Like for example, if you want very high efficiency, you're like, okay, let's not heat the water up too much. Let's say heat it up to 30 degrees Celsius. It's like, I want hot water. Then you increase the temperature. Again, COP will drop, but still would be positive, still would be useful because of the conduction efficiency and ludicrously high thermal capacity. That's why you are improving coupling efficiency and you are solving a problem without requiring, let's buy car radiators, let's pull out an adapter, let's put God knows how many fans into it. Those are janks. Simple. Put it behind the server rack, done. Hot air will go here. It's like, bro, I got this. And once the, let's say, hot water tank is like fully full, start cycling it to swimming pool. Done. So that's why it was like so frustrating. It's like, it's there, just there. Now, reliability is a very core component. If you go to any commercial system and be like, hey, do this and like buy a car radiator, it's like, first they're gonna beat your ass and then their insurance agent is gonna destroy your ass. So for that reason, you have to understand this. People do not want jank. You do not want too many small parts, like, oh, you have like way too many fittings and you have car radiators and you have God knows how many fans. Those fans are expensive. So all those things look cool, but not cool. Literally not cool. So in those sort of scenarios, you want something that is easy to deploy for businesses, meaning you pick a phone, they come and they install, you go home. Ta-da! And this also gives you warranty, meaning you do not have to worry about, like, again, they can put two of them. Like if you are worried about it, so like, hey, what if it does not work out? Or what if I have some very odd scenario where I have very brutal overload? Two systems would be more than competent enough to deal with it, and you can do alternate servicing. So you never have a serious downtime. That's how industrial systems are designed. Again, you can pick up a phone, done. You do not have to jank it. That's the whole point. And plumbing, all you have to do is the plumbing, and plumbing is a known solved problem. It's not a new thing. It's like, oh, how are we gonna do plumbing? It's like, bro, we got this. We got this. We got the pumps, we got the valves, we got the two-way valves, we got the four-way valves. It's done. You can cycle it very efficiently. Heck, I'm not sure whether he has it, but many modern homes have a hot water return line. So if let's say you want your hot water to be hot, as in like 40 degrees Celsius, but if your water remains in the pipe for very long duration, it will start to cool down. So there would be a recirculation pump, something like this size. It will recirculate every 30 minutes or 1 hour, depending on what you set it to, and then it will force the water back again. So fresh 40 degrees Celsius water will be there. So whenever you open the tap, you will never have cold water running and then you have to wait the whole pipe water to flush, then you get fresh water. Nah, recirculation saves energy. So, and again, hot water hydronic heating that he has, like for this type of system, same, he controls it. So control vector is also desirable. You do not want a system that it works or it does not work, or like outdoor temperature controls. Here, yes, it will reduce your efficiency, but you have a control throttle. Meaning if you are, let's say, it's a mechanical room, right? Most of the time is shut down, nobody touches it, nothing is like. But you know, for servicing, few technicians will come. That time you can, hey, let's be human about it. Let's just increase the cooling. And other times you'll be like, hey, let's be efficient about it. 30 degrees Celsius is cool enough. 30 degrees Celsius. So control vector, higher efficiency, and simply non-jank solution was available. And if he does it, I can guarantee you at least 5 or 10 people will try it. And if at least 60% of them have success, then it will become a thing. People will be like, oh, why the heck we did not do this in 1990? Yet this technology is not new. It's just like it took people way too long to figure out. It's like, hey, we can run AC in reverse. So reliability is also a desirable factor here. So this was my presentation on the fact that Linus Tech Tips water cooling makes me boil off. So hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.